and it's a packet. We got most of the front page, with the exception of, I can't remember, the two classes stopped at different places. I think we got to option 4, the rectangles, the six rectangles, and I'm not sure if we got any further. Yes, ma'am? Okay. You were not here Friday. I probably put it on. All right, we're in good shape. 1, 2. We're missing Mr. Todd. Let me do attendance really quick. Oh, I love that. Love to hear that.
She's just trying to brag.
Okay. Sometimes you just have to be proud of what you can be proud of, right? Yeah. Yes. Okay. I heard that. Mr. Josh. Okay, guys, help me out. If you pulled out your homework or your, pages of notes that were stapled together, the packet. Did we finish number 4, the one with the 6 rectangles?
Yes.
Okay, so we're ready to move on to the next page. Okay. Hold on one sec. Gotta do a text really quick.
What is salty? Honestly, this morning I got it's not. Sprinkle it in. I haven't been used to slide by No, I was like in a Monday mood. It's okay. Honestly, yeah, I don't know. But look, so I'm gonna do this chorus, right? But I'm gonna figure that out. Okay, well, I'm gonna put like a galaxy or something on it, and over here is gonna be like that arch. Yeah, it's gonna be like an old arch, and it's gonna go to like I think darkness and black or something, and I'm gonna make be a person right now if I want to put a cat like go to it.
Okay. Oops. This is like so cool. Yeah, it looks like and there's so much. Okay. So we're moving to page 2. Yes?
Yes, ma'am.
Okay. Let me turn the overhead for you so that you guys, we are all on the same page. Hopefully. I think mine is a slight bit different. Organized team kind of. We shall see.
Isaac. Yeah, I met the Bond girl, Kate.
The Bond girl.
She's crazy. She's right out with oh my god.
Okay.
She's just there.
Is this the top of your second page? Yeah. Double checking with you guys. Good deal. There we go. Okay. Big picture. There we go. Okay, you help me a little bit here. This shouldn't be me, like just like with the PowerPoint, walking you through this. Do you remember on Friday get the idea. The goal was to take some kind of curvy function, if you remember, and we started with a parabola, which was fine, nice, easy, simple function for you guys. And we tried to find the area underneath it. And we came up with approximations. Do you agree with that? We never got the exact answer. Agreed? Not of you or something like that. Okay. Now, there is a feature on your calculators, just to give you a little heads up about this, so that you know that this is going to be extremely possible to get a very close approximation. Do you have your calculators nearby? Good idea to pull them out. This will be page 2 of the notes Rob from Friday. I don't. Hopefully you kept it. You got one. Okay, so we're on the calculators. If you guys remember on side 1, the function that we were working with was this. F of x is equal to 9 minus x squared. And when we got down to options 1, 2, 3, and 4, the directions were try to see if you can approximate the area under the graph. We did it 4 ways. We did left-hand endpoints or LHE, we did right-hand endpoints RHE, and we got under and over approximations. You could clearly see which kinds were worse in both directions. Why one was worse, why one was better. Then we did the midpoint one. Then we ended up doing 6 rectangles. Sounds like you guys said you got to that part. And so what I want you to do is think, first of all, if you have your calculator out, go ahead under y1, please, and stick in 9 minus x squared, if you would. Just y1, 9 minus x squared. I want to show you that you're able to do this on your calculator so that in the not too distant future you're able to check these. Of course, please understand that on the AP test, there won't be any that are a calculator question where it would be just plug it in. But I do want to show you this feature because the the test questions will assume, the writers of the test will assume when they write the questions, that you are able to do one of these kind of problems. Okay, now we were supposed to try to find the area between 0 and 3. Are you all looking at a graph of the function? You first have to be doing that. So you want to go to a Zoom 6 screen. Zoom 6 would give you a good view of this. You'd be able to see from -10 to 10 on the y-axis, which is sufficient, and -10 to 10 on the x-axis. Are we okay there? All right, next step I need for you to do. Let me think about my calculator for a second. I'm sorry. I don't want to tell you the wrong thing. I think you want to hit the button. Push the button, please. Second, trace or calculate. So I want the calculate button. So you guys are going to do second trace. There are about 4 major things that the AP test assumes you know how to do when you get to the test. One of which, on the calculator portion, will be doing what we're about to do here. So you want to choose second trace, which is the calculate menu. You guys can see that right above, right above the trace button, okay? And in the calculate feature, in the second trace button, in the calculate feature, is number, I use my calculator, sorry guys, I should turn that on and just do it with you. Second trace, you're going to notice number 7. Now, number 7 looks like something that you have never done before, and I agree with you. This symbol, I haven't talked about just yet. Just understand it for right now, and I'll give you more of a history on it as we go through this first section and into the area stuff that we do with calculus. Just understand that this means we're going to be finding the area under this function and above the x-axis, at least for right now. And then normally, well, I'll just leave it at that. Choose that option. Choose number 7, okay? When you get back to your graph, it's going to, after you do this, choose number 7, select 7, push 7, or hit enter on number 7. It's going to take you back to your graph. And does it say lower limit now?
Yes.
Does it ask you guys for lower limit? Okay. The lower limit means what's the smallest x value where you want to start finding your area. So according to what we were trying to do on the front page, weren't we trying to estimate the area between 0 and 3 on our x-axis? So the lower limit, guys, here is going to be 0. So go ahead and type in 0 and press enter. Or if you just type in 0, it might be okay. And then it'll probably jump to or ask you for the upper limit. How am I doing so far? Is your calculator giving you this, or is anybody getting something different? Because some of you have different operating systems, and I want to make sure. Yeah,
I got upper limit first.
upper limit first. That's weird. That might mean you skipped through lower limit. But if you got upper limit first, press 3, and then hit enter. Does it then say lower limit? If not, you skipped through something. Just do Zoom 6 for me. Start again. Go back to regular Zoom 6. Your axes are off. Do them on. Okay, push second window. second one, yeah, you did second zoom, I'm sorry, it's format, second zoom. Go back and turn your axes on, go back down to here, press enter, and then go back to the word off, press enter. Ah, black, there you go. Now should be good, now you should be able to see. That's probably better, you're like, okay, now this is more. Okay, now do second, trace, and choose number 7, enter. You want to see it did hit lower, type in 0 and hit enter. And then 3 enter. Now, when you guys do the upper limit of 3 and press enter, what do you notice your calculator does? It shades it in. Agreed? What answer did it give you? 18 even? Okay, we are going to find a way in this week, before we get to the end of the week, on how to do this with calculus. But actually, technically what your calculator did is it cut this area into infinitely skinny rectangles, just like we did. But I'm talking many, many, many of them, and approximated the area. So please know that the calculator sometimes will be a teeny tiny bit off of the real answer once we learn the calculus, because it's approximated, okay? It actually doesn't do the calculus. It approximates everything with polynomial functions, in which case it approximates area. So if you've done this correctly, if your calculator's working, you guys need help, let me know. You should get 18 for your area. So you want to do,
Mine just doesn't say any numbers.
it doesn't say any numbers. You have a picture on yours, which is really weird and wild. Go to second, trace again. Choose number 7. That's weird. Type in 0, hit enter. 3, enter. Stop, and then wait for the bottom. It's giving you the area is 18. Okay. All right, so this little symbol, I might as well give you a little hint or a little, like, head down where we're coming from. If you guys remember the word sum, of course you do. Sum means we're going to add a bunch of things, which is what we're doing, agreed? And the first letter of the word sum has to be, or is S. Now, you know from your previous experience in Algebra 2 or Math 3, whatever you want to call it, that we use something in math that looks kind of like a sideways M. We call it sigma because that's how we say the Greek letter sigma. It's about what we're to get to today. Now, the Greek letter sigma, we say it this way, is the capital letter S. And this little shape is basically just an S, kind of like the Old English S, just elongated a lot. That's where that comes from. So it's summing the area. That's where that little shape is coming from. And then the thing that comes behind it means you're finding the area here. And I'll explain to you the whole dx stuff. Just for right now, I wanted to give you a teeny bit of an idea on why that is. Okay? Just so you're like, why is that weird looking shape there? Just understand it means you're summing areas. Okay? Does that help you there? Now, I have a question for you. I want you to think about this without touching your calculators, okay? You ready? Consider the question, consider the function. Don't do it on your calculators. You know something about this graph and its shape. What if I asked you guys to instead go from -3 to 3? Could you do it without touching your calculator for me? I got a yes. Got a yes. We got a could. If the right side area was how big, guys? 18. How big's the whole area? 36. Beautiful. You would just double it. Awesome job. Perfect. Nicely done. Okay, now, do this for me while you have your calculators out, okay? Please type in, go back to y equals, clear it for me. This is not on your sheet. I just want to show you something, okay? So type in on y1, just erase your y1 for me if you don't mind. Type in, please, x to the third minus 9x. Now, x to the third is a different kind of an equation, right, guys? We would call it a what? What's the name of an x to the third equation? What's the short little word for it? Okay, it does have that kind of long run shape, but it also does have a little valley and a little hill. Looks something like, okay, it's supposed to look a little bit more symmetric. Your graphs probably do. Agreed? Does it look like that?
Yeah.
Okay, now, back from your days in algebra 1, 2, whatever that is, if I factor this out and then get x plus 3 and x minus 3, what x-intercepts do you guys see your graph going through? 0, 3, and -3. How are we doing? Okay, now, here's what I want you to do. Ready? Do second calculate again. Second trace, which is calculate. And please again do the area. Lower limit first, give it 0. I want you guys to find for me this area right over here. And upper limit 3. And I want you to tell me what your answer is. And I want you to see what you think about the answer. And if your answer makes any sense to you. What kind of answer did you guys get? You got a negative answer. What is it?
Negative 25.
-20.25. Okay. Next time, I want you to go from -3 to 3. Now, do you agree with me? This graph has origin symmetry. It's exactly the same shape on the top right quadrant as it is on the bottom third, and then the same thing in 2 and 4. Can you predict what's going to happen before you even go through it? I got a nod. You think about it before you type it in. What you just saw is, wait a minute. Below the x-axis has a negative area. Does that mean it doesn't exist? No. It's a placement issue, just like negative numbers on the left side of the number line. They mean left side of the number line. When we see negative area, it doesn't mean that it doesn't exist. It's below the x-axis. So if you guys were doing this problem and it's origin symmetry, right? It's an odd function, origin symmetry. You went from -3 to 3. Please tell me ahead of time what your answer should be. 0. Now I say that because sometimes, again, your answer is going to get stuck in a rounding error, okay? So if you ended up with like 1e -16, you know that's 0.000001 at the end, and you know you should have gotten 0. Because if you guys told me this was 20.25, you can check it. This was negative 20.25. Then this would be positive 20. I can't speak in English, 20.25. And you should get 0. So far, on the front page of this that we've done, we've only looked at area above the x-axis. So what can you tell me now about area above the x-axis, stopping at your x-axis? What sign will you always get? Positive, right? And what about if you go from the x-axis below it? Negative, okay. Now, I'm not going to give you a function for this. I just want you to think about this. What if you had a graph that did something that looks like this, from 0 to 3, and something that looked like this, from -3 to 0? I don't want you to do it because I didn't give you a graph or I didn't give you an equation, right? I just want you to tell me what you think the sign of the total area is between -3 and 3. So between -3 and 3, and again, I know this information, this notation is a little different for you still today, but this is going to be a negative number, right? This is going to be a positive number. Did you see me draw it so that it is not origin symmetry? I clearly tried to elongate this area down here. So I just want you to tell me the sign of your answer. Do you think you're going to get a positive answer? I should put that in not capital letters. Do you think you're going to get a negative answer, or do you think you're going to get 0? When do you get 0? Let me first ask that. When do you get 0 if you would go from x-intercept to x-intercept? When they're origin symmetry, both shapes are exactly the same, right? So do you agree that's out? So do you think you get a positive answer? No. Do you think you get a negative answer? Yeah. Nicely done. Exactly correct. You're getting the ideas there. Awesome. So I just want to try to give you input, kind of insight into the whole area stuff before we actually get into the how do we do it stuff. Ready? Okay, so we're back to this little sheet here in front of us. And we've done the left side. And we're back to the area on the back. Now, big picture. I tried to summarize in parts of these notes as we go through. And for the most part, we're going to go through the majority of this. To find the area of any rectangle, and I'm going to, when I fill this in, I'm going to fill in your, are you kidding me? That was pretty good. All right, now, to fill this in, I was going to use orange. I don't think you need my help on the very first line. How do you find the area of a rectangle? You have 2 lines. You guys can choose to do it in one of 2 ways. When I say if you were tutoring a geometry student, or student in geometry, or middle school for that matter, how do we find the area of a rectangle?
Mrs. Samachino, will you please call 3715? Mrs. Samachino, call 3715.
She said it twice because I didn't catch it first. Okay, how do you find the area of a rectangle?
Length times width.
Okay.
Times height, just
Good, that's what I was getting at. That's exactly right. If you would prefer to write it as length times width, that's totally fine. If you guys would prefer to write it as length times width base times height, completely fine with me. We get it though, right? We know we multiply in 2 dimensions. Agreed? Doesn't matter which way you want to call it. So, the second sentence up here is just talking about what we mentioned on Friday. You tell me, when we did these approximations, and I think if you look at the numbers from the front of your page, this is pretty close to when we did 6 rectangles. If you wrote down your answers from Friday, is it pretty close? Now this is the exact answer. Remember, when we did 6 rectangles on Friday, we got an approximation. But what I want you to see is that adding more rectangles does what to your approximation? Circle one. Or I should say, to get a better estimate for the area under the curve, choose more or less. More, exactly. Okay, so easy there, circle one, the more little skinny rectangles we cut this in, the less error there's going to be. Make sense to you in your heads? Now our goal is to be able to do this with infinitely many skinny rectangles, like almost rectangles as thin as a piece of dental floss. Okay, so now here's where we're getting at how this all sort of fits into place. Because you are in AP calculus, you guys need the theory, a little bit of the theory behind why we get what we get. So underneath this, it says if we choose to cut an area into n rectangles and use the right-hand estimate, how do we find the area? So let me draw a little picture here.
RHE estimate?
Remember, on the front side, we had a picture that we cut into, first of all, we did it this way. I think when we drew the picture, every single time you drew it, it was drawn on the first rectangle, or it was drawn on this, looked like that, right? So here's the idea. Instead of cutting into n rectangles, but what we did the first time through, if we use right-hand endpoints, just to review with you, you can look at the front of your sheets. If we use right-hand endpoints, it would have looked like that, and we would have found, remember me talking about area 1, area 2, and then it's going to be kind of a little hard for me to talk about area 3, because how big is area 3? If we use right-hand endpoints, it'd be like non-existent, right? It was 0, if you remember that from Friday. Okay, so if we choose n rectangles and use the right-hand endpoints, how do we find the area?
Oh, okay.
Well, you're going to be adding, yeah, go ahead.
I was gonna say, like, we could say, like, I don't know how I'm gonna word this.
I know, go ahead, take some time, think about it.
It's like 3, wait, yeah, I guess, not necessarily 3, but like 3 divided by n.
Tell me, stop right there, you guys listen to Rob. Rob said 3 divided by n, what does that represent?
That shows how many rectangles you're gonna be able to have in that area, right? No.
You're
Minus
close. You're close. No, you're close. I don't know that it says how many, like, in this case, it tells me 3 rectangles.
Yeah, because there are
I
3.
mean, I know the last one is non-existent, but 3 rectangles. But what does 3 over n represent?
I mean,
You're on the right track, Rob. You're doing really well.
trying to word it.
You're doing great. That's why I said take your time. You're thinking. You're on the right track. Okay, so let me ask you guys this. When we did this on Friday, how did we find?
You know what I mean, the
Go ahead.
base.
Yes, that's what I was waiting for you to say.
That was what I meant to say.
That's the width of the rectangle.
Yeah,
Good.
base of the rectangle, then
That's
you
right.
multiply that times f of n.
Right. Well done.
Well,
Plug that
well,
in. Yeah. Okay, you ready, guys? Do you remember this from the other day? This point up here was 9. I believe this point was 8. Is this sounding right from what we did on the front of the page? That's 8 when we plugged in 2. This was 5. And when we plugged in 3, this was 0. How am I doing there? Okay, here's my question for you. If we're doing the first rectangle, how did we figure out what 8 was? Didn't we take our function and plug in 1 and do 9 minus 1 squared and come up with 8? Do you see that idea? How did we get f of 2? How did we get this height right here? Well, we plugged in 2. We did 9 minus 2 squared and we came up with 5. So what I want you to see is that each time we do this, to get the height of a rectangle, no matter where it is, we're going to plug in whatever your x value is, plug it into the function, which is what Rob was just talking about, and our function here was 9 minus x squared. And then we're going to use that, and then we're going to obviously multiply by the width, and we're going to tell whoever it is how many of these rectangles we have. Are you with me there? So here's the idea. Remember earlier today we said maybe base times height is a good way to look at this, because again, I want you to think about this. We're cutting this into lots and lots and lots of rectangles. Let's just use the first one. Let's look at this one. What if I said that's like x1 right there? Okay. If that's x1 and I'm approximating the very first rectangle with x1, that's my width right there, then what's this y value right here? It's just f of x1. That's what I would get when I plug x1 into it, whatever the heck x1 is. I'm saying x1 because these are going to be many, many, many rectangles, infinitely skinny. So I'm going to have x1, x2, x3, x4, it's infinitely many. You follow me there? Now, how wide is this right here? Well, is it just x1 units wide? Okay, so underneath this, to do a right-hand endpoint estimate, then I want you to put down for me, we're going to do the function evaluated at the right-hand endpoint. I'm skipping a space here on purpose, just heads up on that. See if this makes sense. That's RHE for right-hand endpoint. Look at what I did over there, look at what I did over there. I'm plugging in the first right-hand endpoint to get the y value, so that's my height. And then the width of this would be delta x. So the way I'm doing it is just Because in calculus, you're gonna see the f of x in front, and you're gonna see the dx in the back. So that's height times the width. And then in front of this, I want you to put a sigma. Now, we haven't worked a lot with sigma yet since pre-calc, but we're gonna start reviewing it. It's not gonna be all that bad, I promise. It'll be fine. Sigma means you're adding a bunch of stuff, right? Because we're adding a bunch of rectangles. Now, how many are we adding? Well, we're adding, in this case, what we wanna do, now, you might remember this. When we do sigmas, oftentimes the bottom number of the sigma, we use I, and I don't mean the square root of -1, I, J, K, something like that to represent which place or which term you're on. We'll use I equals 1 here. I'll just stick with I because usually that's the case, but sometimes we use I, J, K. Please remember that doesn't mean square root of -1, okay? That just means that when we do this, we're going to have x1, x2, x3. It just stands for your subscript. You know what I mean? You're going to have a bunch of these, okay? And then this is going to go up to n. So that would represent how we would have n rectangles. So see if this makes sense to you. This expression right here is height times width of one rectangle, okay? And this is saying always do the right-hand endpoint times the width delta x. Okay, now delta x doesn't refer to from the x-axis. It refers to like the distance between the previous x and the x that you're on. You follow what I'm saying there? Now, what I'm doing here first is just writing how we would cut this into n rectangles. But I don't want to just think about how to do n rectangles. We want to think about how to do this with infinitely many. So for right now, just know I'm headed toward trying to make n. Did you hear what I just said? We want infinitely many rectangles. So what do I really want n to stand for in the end? Infinity, that's right, that's where we're headed. That's exactly right. Okay, so we're not there just yet. Now, we're on consider a particular case where we selected 4 rectangles as we did above, but we're going to generalize here. So when you guys get to here, I'm not giving you a function. F of x could be anything at all. I'm not giving you your y equals. No longer is it a parabola, it's just f of x. Are you all right with that idea? What if we choose an arbitrary number of rectangles? Yeah, we're on consider a particular case where we have 4 rectangles, but we're going to generalize here. So the right-hand endpoint. So here's the idea. You have a picture, and I don't even know what the graph looks like. It doesn't have to be a parabola. That's what I'm trying to say. Could just be area under a curve. Are you following me there? And it doesn't always have to start at 0. I want you to kind of think about this. You could start maybe here and end maybe over here. So what we normally do in calculus is kind of talk about start to finish A to B. When your calculator on your, remember earlier it asked you for the lower limit and the upper limit? Remember when I had that written here? We'll call A the lower limit, the one on the left, and B the upper limit, the one on the right. It doesn't mean like it's stacked this way. It just means small x to big X. Does that make sense to you so far?